Hello and welcome to our talk on ordinals in HOT. Ordinals are fundamental and useful, for example, for proving termination by exhibiting a strictly decreasing sequence of ordinals, or justifying induction and recursion by using ordinals to iterate until you reach a fixed point. Unfortunately, they are also constructively problematic in the sense that the classical notion fragments into many inequivalent constructive ones, each with their own pros and cons. So in this work, we consider 3 different constructive notions of ordinals and we relate them to each other. The first one we consider can be found in the HOT book and in further work by Escado, and is inspired by work by Paul Taylor. It's the one that's perhaps most closely related to the set theoretic definition, where we consider an ordinal to be a type together with a relation, which we can think of as the epsilon relation from set theory. So it's transitive, it's extensional, meaning that elements with the same predecessors are equal, and it's well-founded, meaning that every element is accessible, where accessibility is an inductively defined notion. We can also give an order on this type of ordinals themselves. So if we have 2 ordinals x and y, then we say that x is smaller or equal to y if there is a monotone function from x to y, which satisfies the simulation condition. If y is below something in the image of f, then y itself is in the image of f. And such a monotone function is necessarily unique if it exists. We say that x is strictly smaller than y if there is such a simulation which is bounded, in the sense that there is some bound y, and such that f induces an equivalence between x and the initial segment below y and y.
In the usual inductive definition of Brouwer trees, there is a supremum constructor to form a new tree for every countable sequence of trees, but we cannot identify the trees that represent the same supremum. Our second notion of ordinal is a type of Brouwer trees that can faithfully represent ordinals and can classify an ordinal as zero successor or limit. We define Brouwer trees as a quotient inductive-inductive type. Their order relation is defined simultaneously. As in the usual definition, we have constructors for zero and successor. In order to distinguish limits from them, we restrict the limit constructor for only strictly increasing sequences. We have a path constructor saying that bisimilar sequences have the same limit. In this way, our notion of Brouwer trees can faithfully represent ordinals. The constructors for the order relation just ensure its desired properties, such as transitivity and that zero is minimal and so on. It is well known that each ordinal can be uniquely written as a finite sum of omega-based exponentiations, such that the exponents beta 1 to beta n are decreasing. This is so-called Cantor normal form, and our last notion of ordinal is based on it. We work with the unlabeled binary trees. For example, alpha can be represented by such a tree. We work with the lexicographical order on the trees. Then we can define a predicate of Cantor normal form to express that beta 1 to beta n are decreasing. Then we get a subset of trees in Cantor normal form.
We now have 3 different types that implement ordinals. It turns out that they share a couple of properties. Firstly, they are all well-founded in the usual constructive sense, and they are extensional. One of the technical challenges that we faced was to define the type of Brouwer trees such that it is well-founded and extensional at the same time. Next, for each of these 3 types, we can define the usual arithmetic operations. Exponentiation does not seem to be constructively possible for extensional well-founded orders. But the actually interesting bit is that the operations satisfy the same specifications, even though they are defined very differently. For example, addition on Brouwer trees is continuous in the second argument by definition, but for Cantor normal forms, we can't even calculate limits, and this property is much less obvious. Okay, so let's finally look at the differences between our 3 notions of ordinals. Most properties, such as equality, are decidable on Cantor normal forms. For extensional well-founded orders, they are not decidable. Even deciding whether an element is 0 is already equivalent to the law of excluded middle. And finally, Brouwer trees sit in the middle. We can, for example, decide whether an element is finite, but we cannot decide equality in general. Since we can define these arithmetic operations on Brouwer trees, there's this canonical map, and it's injective. It also commutes with the arithmetic operations, and it's bounded, since every finite tree represents an ordinal below epsilon naught. Good, so since the order on Brouwer trees is extensional and well-founded, we get such an order by taking all trees below a given tree, and this is what gives us the second canonical function. Again, it's injective. We cannot show that this function preserves the arithmetic operations, at least not constructively, but it over-approximates them. And also it commutes with limits, but not with successors. That's actually related to the next point. It's not constructively a simulation, as that would imply WLPO, but if we assume excluded mill, then it is. And finally, it's bounded again. Okay, so this was a summary of the main results of our paper. Many thanks for watching.